Okay, if I can get you guys to come to order. So welcome to the September NCGS meeting as we resume getting together. I'm Jim O'Brien, the president of this august organization. Great turnout tonight, which we really appreciate. We're going to start with a couple of special items, and then we'll go back to our sort of normal program, which involves having announcements and introduction of guests and that kind of thing. But first, and most importantly, we'd like to call Dave Blanchard up to present an award to our very own Ray Sullivan.
Thanks, everybody. Can you hear me? Okay. First of all, I thought what we would do is tell you what this award is about. And this is an AEPG award, and it is the Presidential Award for Exemplary Service presented to Raymond Sullivan. And let me just read you the letter here. Dear Raymond, it is with great pleasure that I present you the AEPG Presidential Award for Exemplary Service in recognition of your long-standing dedication to educating students. You are highly regarded for your strong commitment to geoscience and to making the world a better place. And on behalf of the association, we are truly grateful. Signed by Stephen Goolsby, the immediate past president of AEPG. Now, we can leave it at that, or I just want to say that there were so many people, a lot of people in this room, in fact, really went to bat for Ray. When we started off this process, probably 5-6 years ago, and then COVID got in the way and things like that. It was just a fantastic journey. One thing, Scott back there, Scott Morgan, Jim Nickus, former students, we were over at Ray's, and Barbara had prepared a lovely lunch. And we got talking about this, and it was just stunning to me and to Scott and Jim, just how much Ray had accomplished during his life and his career. I mean, he was pulling out books that he had written in the 60s for like elementary schools and middle schools about geology and life science and biology. Who knew, right? I didn't know. Did anyone else here know? No, I know. Yeah. And, as we got through collecting papers and different sources and that, we realized that Ray had been voted the most inspiring instructor at San Francisco State University 5 or 6 times. Incredible. And, some of the comments that came back from the students that had written, in support of Ray, were things like inspiring teacher, helped me achieve my goals, all these sort of things that just really gave you the idea of what a great teacher that Ray is. I know, speaking personally, I was a music major at San Francisco State. I still play guitar. But when I took Ray's class on the geology of national parks, I was just captivated. I was captivated by, Ray and the way he presented it, the field trips we went on, and everything that he did to make it an exciting and a very meaningful course. And so it was just amazing. Ray also, he would take students on the weekend, on his own weekend. He'd take students like myself and others in this room out on field trips. Sorry, Barbara, but yeah. But I mean, that's where I met Morgan when he was just, I don't know, he was only about that tall. But he really put a lot of his own personal time and effort into teaching students. But as we all know, it's not just students. He's written papers. Is the latest book that he was editor of and wrote for the geology of Mount Diablo is a volume that'll stand for decades. And he also really enjoyed earthquakes. I don't know why you liked earthquakes so much, Ray, but but he really took a shine to earthquakes. He did a lot for different institutions and educational institutions around the country for earthquake education. Reams and reams of letter of thanks from institutes as far as like Chicago, back east, LA, you name it. But it was just incredible. And then also, as we know, he would do field trips to Mount Diablo, and then his famous field trips down to in San Francisco in the Embarcadero, where it was all bay filled. In fact, I don't know how many of you know that we're dealing with a TV personality right here. He had a cameo appearance in Engineering Catastrophes, where he was interviewed, right? He was interviewed on that show to talk about these buildings that were starting to lean and tilt and sidewalks that were, you know, offset by these faults. So he's done an incredible job, and you know, there's the students he's had. They've gone into the oil and gas business. They've gone into education, academics. They've gone into the environment. They've gone into all sorts of things. And so he's really inspired, I would say, at least one or two couple of generations of people to really excel in geology. And some of the students that he had, like me, took his class and were so inspired, they became geologists too. So it really was just a remarkable thing. And then interestingly, his son Morgan, yeah, when he was teaching at the Chico, right, you did a similar thing. You said, I think there's two students of Morgan's in the background. Here we go, 1, 2, 2 former students of Morgan's there. So the tradition continues with Morgan. So I'd just like to say it's been an honor for us who have the people like Don Lewis as well, helping out, writing support letters and getting everything together. But we all did that out of our hearts and out of knowing how much you meant to our lives. So thank you, Ray.
It's our honor to have you be part of our group too. All right. Ray, you want to take the words? Okay. Well, I think we've taken an awful lot of time, but I really appreciate all my former students. I appreciate being part of NCGS. I enjoy all the roles I played, and Don, when we were gathering, it came to me to gather all the materials that he wanted from me. I just gave Dr. University, and I just gave them. He said, here you are. And when I told Don this, and I just mentioned this tonight, he said, you're not going to get a teaching anymore. In 20 years since you've been in a classroom. So tonight I didn't have to, and I wasn't going to come tonight, even though I really wanted to hear the talk, something I've been looking forward to, because Ron promised to give it, not once, I tried to say to do a paper for the drawing. But anyhow, I and I just would like to say that I can't name everybody, but I thank everybody who wrote my talk. Thank you very much. That's my dear wife.
Back to you, Jim. Thank you.
Yeah. Okay. Very good. Okay. Thank you, Dave. We appreciate that. One other special item before we start our regular program. Ross Wagner, could you come up, please? Ross is also one of our contributors to the Mount Diablo volume. I love the map. I've been working with that in the East Bay here for a couple of years now. But he's got a special request. He would like some technical help. So I'm going to let him speak to that specifically, and we'll see if anybody's interested. Go ahead.
All right. Yeah, I want to afflict all of you now, and I'll do so. I've got resistivity and SP logs from a well up in Sonoma County. I'm sorry, I got it closer. Which one is working here? Okay. I have a resistivity and SP logs from a oil well up in Sonoma County in an area that I'm currently working on. And if my somewhat unsophisticated interpretation is correct, the information from that log will considerably change the local structural interpretation and maybe our interpretation of the amount of displacement on the Hayward Fault. In way of just very quickly, way of detail, the Petaluma Formation is a formation that's up in northern Sonoma County, and it's younger than 9 million years. There are plenty of radiometric dates. The area I'm working on is in a thing that's called the Petaluma Formation, and from a lithologic perspective, it's reasonable, but it's overlain by a basalt that has two dates of 10.3 and 10.2 on it. So it's much older than the Petaluma in its sort of type section further to the north. There's about 30 meters of section exposed below that basalt, but this well, if what I think is correct, has 3,400 feet of that kind of sediment underneath this 10 million year old basalt. And that would really change our understanding of that particular area if my somewhat unsophisticated interpretation is correct. So if anybody would be willing to spend a couple of 3 hours on something like that, I would be very appreciative. I'll be here, and I've got further information. You can talk to me after the meeting, and I'll turn it back to you.
Thank you very much. Okay, this sounds like a real opportunity. We've got plenty of people in this room who can help with that, so please step up. Okay, let's go back to our sort of regular order, as they say. First, just a couple of announcements from the president. The board has been busy the last part of the summer, and you may have noticed some of the differences already, which is that Don Medvedev has dragged us kicking and screaming into the 21st century with new technology for our website, so that we now can register, accept payments, send out newsletters, do all sorts of things through a couple of rather sophisticated platforms he's put us on. So we appreciate Don's efforts very much. You should have seen some notifications about this, both in the newsletter and elsewhere. Don, is there anything you want to say specifically about it?
The only thing I guess ask, if anybody's had any trouble with it, send me an email. I fear that people who have trouble with it won't get in and won't know that they're having trouble. Bit of a catch-22, but so far that I've talked to has not had a problem, other than the email system that's now sends out the newsletters comes from one of these no reply sites. So I fear possibly that some people have email servers that see that and see that it has a link and clears it, sends it to your spam. So I'm not sure what I can do about that, but it'd be good to know if there's a problem or not.
Okay, very good. Thank you.
I will, I'm Will Fuller, field trip coordinator, and I will compliment Don. Tom McKinnon and I, mostly Tom, ran a second run of the Point Richmond, Point Malate Trail field trip since the June meeting.
Yeah.
And Don set that up and said, we're just gonna do it all online, and I went, oh no. Flawless. It filled up. It actually even occupied, I think, one spot of the wait list, and then it popped back down when we lost a person. So, boy, it sure does bring us to a whole different realm of
Good.
I have a page I've already implemented. It will be published, I guess is the word, in the spring when we do the dinner meeting. So you won't have to send in a check for the dinner meeting. And we won't have to do that like 2 weeks in advance, because we only need to do the dinner order like 3 days in advance. So we just have to have the deadline 3 days in advance.
Anyway.
Will, while you have the floor, any other announcements about field trips for this? No?
So there's a group of people working toward an Angel Island field trip. Several of you over there. And there's all sorts of logistical issues, plus Christy,
Row,
who's back in Eastern Canada.
McGill.
Is our kind of chief resource. So there's going to be a small group of people going out with her in December to scope out what they're finding in terms of really up-to-date geology. And then sometime in the spring, depending on logistic weather and all sorts of other things, we will start offering that trip, probably multiple runs. So something to look forward. We've tried setting that up for years, and it's finally looks like it's gonna come to fruition.
You just mentioned that we're trying to get trams for that.
Yeah, well, that's part of it, yeah.
Right.
Yeah, and some of us actually don't like to walk 4 or 5 miles.
Okay, very good. Thank you. Before I go any further, introduction of guests. I know we have some guests here tonight, people that are not normally here. We have some young people over here. Raise your hands. Who are these folks? These are Owen, Andrew. Yeah. Okay, very nice. Welcome. Thank you. I know our speaker, who hasn't been introduced to you yet, will be shortly, but his wife Kathy is here. Kathy, could you stand up so we can say hello to you as well? This is Kathy Lowe. Anybody else? I know we have some students here that I don't think we normally see. You guys introduce yourselves quickly.
I think I'm your newest member. I signed up today.
Excellent. Hey, excellent.
One of Morgan's former students.
Welcome, Ryan. Okay.
No, he survived.
Good evening, everyone. I'm Steven Springhorn. I work for the California Department of Water Resources in Sacramento, and also a student of Morgan's. So happy to be here, and I'll also be signing up to be a member.
Great. Great. Excellent.
Scholarship.
Oh, excellent. So all comes back around. That's good. Okay. Anybody else? Greg? Okay. Come on up.
Several things here. This is the start of a new academic year for many students. The NCGS has 2 scholarships for graduate students. They're $2,000. If you know a graduate student working in geology or some related field close to geology in Northern California, please advise them that there's a scholarship available. This has been sent out to every university and college in Northern California, that's including St. Mary's, and schools that don't have graduate programs also. So this is sent to the chairpersons and the person in charge of graduate coordination, and hopefully they pass the word along. But we don't know until the applications that the student writes start showing up in the mailbox along about December 1st or so. There's no formal application. They follow the instructions on the page. If they write a well-written proposal, there's a chance that it'll be considered. If they can't write at all, or don't know what they're going to be doing, it probably won't be accepted. So that's the difference. In other words, sometimes some people just write better, organize themselves, and tell us what they want to do and how they're going to do it. So that's another thing. So another thing back there's a table full of books. These have been donated to the NCGS by Tridib, a former member, and some other people that used to participate in NCGS activities. And the price is you pay what you think it might be worth, in other words. But the thing is that come Christmas, there's going to be no boxes in my garage left. So I got 10 more boxes. So if they're not going to be taken, then they're going out some other way. So thank you.
Thank you. Let's see, other announcements. Over the summer, I took the programs that we recorded last year on Zoom when we were still doing hybrid meetings, and they've now been uploaded to a YouTube channel that's called NCGS at 1000. That's our aspiration. We'll get to 1,000 speeches one of these days. But in the meantime, if you go to YouTube, you can look these up, and they're all live now, with the exception of one where I haven't gotten permission from the author yet. But our intent this year, as you probably saw in the newsletter, is we're not running hybrid meetings anymore. We're running them here in person with an in-person speaker as much as we can. We're still going to record them to the cloud. I will still upload them to the YouTube channel afterwards, so it'll be accessible for members to go back to, or to refer friends to, or to, in fact, use in the future. So we appreciate the interest in seeing some of these. We're actually putting a poster together of the talks that are on the schedule that are coming up, because we have 3 new program directors that are doing a bang-up job, much better than I was doing. So I'm glad to have them on board. And they've got a schedule already for most of the year, and we're going to advertise that to the schools in the area as well, so that they know about it. Take a look at it. Good. Okay, great. Okay, other announcements. Andrew, I know you wanted to say something.
Howdy, it's nice to be back. I was your speaker in June, but I'm here as the NCGS webmaster. I have been trying to transfer our website to a WordPress server, which will be much faster. I'm going to give up the old design, which I consider very clumsy. And so I have been cleaning up everything in the past. And I want to say, since we're talking about Ray Sullivan tonight, that I've gone through a lot of field trip reports, and which we have PDFs online. They're going to be preserved as long as the web shall live. And Ray's stuff is there, you know, with his beautiful downtown San Francisco stuff. It's there for anyone to download for perpetuity, you know. And so that's a really cool thing, and it's a privilege to clean all that stuff up so that webmasters from now on will have a very simple rubric to figure out what's what. My goal is to change over in early October. The design will look different, will not be the same, because we can't. Our old design was commissioned from a professional designer. The new design will be my design. It will be simpler. But what I want to invite you folks to do is, I'm looking, you know, as I was revising our old field trip reports, our peak year of field trip reports was 2006. And at the time, imagery, you know, bandwidth was a big deal. We used tiny little images. Any of you who supplied photos for those old field trips, it would be really cool if you could look back in your records and send bigger copies. Maybe you've learned how to clean up your images, you know. We can fix history. So please take a look at the existing website. The new website will have all the old stuff there. Probably not immediately, because I've got to just build it and launch it. But I've scraped it all down, and I have it all on my desktop, and I'm working on that. And this is an opportunity to make the whole thing better. So thanks for that.
Thank you. Okay. Are there any other announcements? Okay, I'm going to invite Greg Bartow to come up to introduce our speaker.
Thanks, Jim. So I'm here on behalf of the program committee, which we used to just have one person, which last was Jim O'Brien. getting speakers, but this year it's taken us 3 people to fill Jim's shoes, and that would be Paul Henshaw, who's here, and John Karachuski or not, and myself. So I want to welcome all of you to our first speaker meeting for the 23-24 year. As I said, there's schedules on the back if you want to grab one. Before I introduce Don, let me just say next in October, the speaker next month is Linda Dismore Swift, talking about climate change, evidence, and possible tipping points. And that's on October 25th. It's my personal pleasure to be able to introduce Professor Lowe. It's great to have him speaking. What a great talk we're going to have for our kickoff meeting for this year. Let me tell you just a little bit about Don Lowe, and that is that he was born and raised in Sacramento. He received his BS degree from Stanford and then his PhD from the University of Illinois. After working as a postdoc for the USGS, he returned to the academic stream in 1970 as an assistant professor at Louisiana State University. In 1988, he returned to Stanford, where he served as a professor for the last 35 years. He has received numerous awards and is a GSA fellow. Don is a geologist with 2 main long-term professional interests: the Archean Earth, which we're going to hear the talk tonight, and then deep water sedimentation. The latter led to the study of deep water turbidites dominated sequences in Western California, Arkansas, or in California, including the Pigeon Point Formation, which I'll talk about just in a minute. And then also in Arkansas and Oklahoma and the North Sea and many other places around the world. His focus has been on the process of sedimentation and how they reflected in the resulting deposits. The other main focus, which we'll hear about tonight, has been his early Earth, mostly the Archean prior to 3 billion years ago, where he's worked in South Africa and Western Australia. The goal has been to develop a picture of early surface environments, early life, and what it was doing, and characterizing the nature of ocean and atmosphere, and including development of evidence that the early climate was hot. So I'll have to say it's especially a pleasure here to introduce Don. I work, as some of you know, part-time for California State Parks, and one of the jobs I was working on was at the Pigeon Point Lighthouse. They had a 10-foot deep well that was the Coast Guard operated since the early 1900s, which is not sanitary, and the state said, no, you can't use that anymore. You have to put in a deep well. And so in a bedrock environment, we were drilling and hitting dry holes, and it was terrible. And then I found out that Dr. Lowe and his students had done mapping there and really knew a lot about the formation. So I contacted him, and he was so kind to come out, talk to us, share his mapping, look at our data, and really helped us come up with a strategy. And we did drill a well that was sufficient to supply the park and the hostel. And we were in jeopardy of having to close down the hostel if we didn't have a water source. So it was really good. He also did some petrologic analysis of the cuttings and helped weave the story together, and helped with actually a handout that we use for the geology of Pigeon Point, which is on the state park's website. So with that, let me, Don, thank you very much. And a round of applause for Dr. Lowe. Yeah.
Thanks a lot, Greg. And thank you all for coming out this evening. I want to thank Jim for inviting me and taking my wife and I to a really very nice dinner. And it's just good to see everyone. I've met a lot of people here who I didn't know were here, that I've known from years past, mostly in turbidites, but that's another life. All right, I want to get on with it this evening and talk about the Archean. This is a period of time that I fell in love with after going over and looking at some rocks. Can you hear me back there okay? Okay, I'll try. Get up a little closer. Is that better? I just want to make sure you can hear. I hate being confined. I like to pace back and forth and do all sorts of things as I talk, but I guess I'm here. Yeah, maybe I can. Hey, look at that. Yeah, now I can really go. But I have to stay in front of this camera.
Stay in the view of the camera.
Yeah, yeah. Okay.
Nice.
It may be one view this evening. All right, well, while Jim's getting that set up, there we go. So what did you press, Jim?
I just pressed the mouse on the each slide.
Oh, okay.
Next.
No. Well, if I come up from behind this, yeah, here we go. I can carry my microphone. Okay, I created others and said something about who I am. Sedimentary geologist, I work with sedimentary rocks. And we get out and work with the Archean and the sequences that are preserved in geologic record. I'm afraid I spent more time walking over drainage. But there are sediments that are better than this video I'll show you some examples. And what I'm trying to do in the working with these Archean, you know, what was the Early Archean? I mean, this is far back in geologic time as you can. As a sedimentary geologist and student of historical geology, I immediately looked far back as I could see. I tried a good job how far back you could go. You know, there are two groups of people who look at things in ancient times. Cosmologists who look back billions and billions of years in time looking out in space. So resolution, critical. One of the things light years ago. Geologists look back billions of years. But those are looking very far. If you're all big picture, the big picture, cosmologists have to worry about 500,000 small. Looking back in time is something about just trying to get time and trying to resolve this really clear show. We're looking at some of the oldest well-preserved sedimentary surfaces, 3.6 to 3.2 billion years old. Everything older than that is cooked. From my perspective, cooked too much. The really didn't talk to people. So what do I want to discuss today? I'm going to give you a couple of sort of definitions. I'm pretty sure people do know what the Archean Earth give you a definition. What a greenstone belt is. And then I'll talk. I don't want to keep you here all night, so I'll also skip a slide here and there and cut things off as we go. I want to tell you a little bit about some of our discoveries. First of all, the Lowe of impact in early history. One of the surprising things we found, looking at the top, is there were layers of stuff in them that was ejected from the humans. And I'll show you some of this stuff looks like. Here's the still being white by a giant asteroid. It's up to 50 kilometers across. It's done for 2 million years. Every bombardment may have ended, but the late stages of large scale bombardment are still going on. I'm going to talk about the surface temperature. We have done a topic work on surface and really lots. You think the surface temperature was probably about 70 to 80 degrees Celsius. So we've been down right in the front. This has been the first presence back in the 70s and a very controversial issue. We kept trying to refine our measurement. This publication in 1920, 1921. Use triple oxygen isotopes and shows still safe. If I have a chance, I'll show you the pictures of life on Earth. You guys will also see pictures from my building. Let's see our kid. Stage and rocks down at the bottom of the Grand Canyon. Archean is a period of time that lasted from about 4 million years to about 2.5. Folks watch the bottom of the Grand Canyon. Very young.
compared to what we talked about. And so we're back looking at, most of the rocks on 3.2 to about 3.5 kilometers. And it's hard to read this chart, but it's way over on the column on the right-hand side, down here in the bottom, you see the Archean. Right down in here. It's actually subdivided into 3 different units that we won't have to worry about. But much about the work with failure. They're only and we work in walk across what are called gravestone. Here in Brava, you see gravestone, not crossing the wall. The green volcanic rocks, and then altered green minerals. And there's plenty of gravestone. Once you get back the ways of time, there's nothing left of these. Okay. And so when you go back into the early Archean, you're having a choice about what you work with, if you're starting with geology, work with rock, and then any volcanic. So greenstone rock is stacked volcanic rocks, mafic volcanic rocks, interbedded with often in sedimentary layers. And that's what rocks of this instance. There were no nice proton covers, there's no quartzites, no carbonates, none of the stuff that we would love for looking at in the Great Basin and the portion of the stuff that people volcanic. If we look at the average piece of continental crust and say, what are the gravestones? This is a column of the Grand Canyon. You can see at the bottom of this diagram, there are 2 main rock units. There are the rock units in sort of purplish color, and it's a Vishnu schist. Those are greenstones. They have been altered to heck. And the orange stuff that kind of intrudes some of the fingers growing up, those are granites. So most of these Archean belts we work in are granite greenstone belts. I drive across the granites to get to the greenstone and hope they're not too metamorphosed. Then up above we have proton cover sequences, which is where everyone likes to go for fossils and for sediments that aren't cooked. And so we're really peering back at the oldest roots of 1 to 2 oldest protons in the world. Capital Croton in South Africa is 3.1 billion years old, and all of the rocks within that Croton are over 3.1 billion years old.
Yeah.
There, yes. Okay, so Vishnu schist here and this purplish here, all form, show you what they look like. Here's the Grand Canyon. Most of you have probably been there, marveled at it. Look at these great layers of geology up on the top. That is the Tom Cover. Great stuff. Down here, in the inner gorge, it's a messy stuff. Comes to the basement, and it's made of granite and granite. Most of the gravestone part in the Grand Canyon belongs to the called the Vishnu schist. It was really fantastic. About 10 o'clock, so it's in the sediments. If you go down the river, you go to the different perspective, and all of this rock making up the walls of the inner core, the black stuff is to the meta-volcanic and meta-sedimentary. Most of these younger things from 63 are so metamorphosed, and most importantly, they're straight. So they can be sheared, and all of the good sedimentary features get lost. As you see, in South Africa, this is stuff that's 3.4, 3.3 billion years old. So it looks like what we have in pigeon point. You're looking at sandstone, shale, the pictures, you can see the ship. Beautiful pictures. Early Earth. So, if you like the time, 4.5 million years ago, the Earth formed over about there. And here we are today. You can see the Phanerozoic occupies all of them. Paleozoic, Mesozoic, Cenozoic. Let's just go with 1 end of the scale. Then there's a long period of time called Proterozoic that I'm not even going to talk about. But then we get to the Archean. Thing to remember, look at the slide, is the green or greenstone belts. And the yellow is Cretan cover surface. And you can see once you get back before about 3 billion years, between 3 and 4 billion years, there's no the time when we haven't formed any Cretans yet, so we can't have any Cretan cover sequences. Only when we form these first Cretans here, do we get a nice solid continental block on which we can deposit stable shelf type of sediments that we're so used to looking at on the record. You guys in California here are kind of special because Western California is not a Cretan covered world. If you were from the mid-continent region and you're used to driving across the West Texas, we go mile after mile after mile, flatline limestone, or the Grand Canyon, you're all these flatline units. You're used to working in Cretan cover. Here in Western California, we don't really have a Cretan below there. So there's no Cretan cover. We're in essentially a mobile here. And we haven't stabilized this block by forming a continental basin. So we don't have a continental sequence on top of it. So California's been special. The sequence that I'm going to talk about is this part of the greenstone belt in South Africa. This shows on a global scale the distribution of Archean rocks and large blocks of continental crust that are of Archean age. You can see all of these in here. The white rocks around them are mostly young. Proterozoic, Paleozoic, Cenozoic, things like this. And the gray areas are exposed basin to basin. What a basin for a basin? They're still down into the roots of the continent. Something called basement. And that's what we're saying. Rocks that I work with mostly are over here in South Africa. Called the Catball Cretan. It was one of the oldest blocks of continental crust. So here we are, Central map of South Africa. There's a Zimbabwe Cretan here. It's by and large younger, it's a late Archean sequence. But this Catball Cretan stabilized at 3.1. I'm going to blow this up. So here is the outline of that Catball Cretan in Southern Africa. Here's the Indian Ocean, and over here somewhere is the Atlantic Ocean. The basement is only locally exposed, mostly covered by Cretan cover. So all of this yellow and green, purple, these are all mostly fairly flatline sediments and sitting on top of the basement. Here outcrops of the basement here and pieces sticking up there. 3 to 4 is a big impact structure. So meteorites smacked into the earth and exposed basement. This little bit of yellow right here is part of the greenstone belt. That's what I want. It's over here in the eastern part of South Africa, so we fly into Johannesburg and drive across the border. I don't want you to don't panic. Really don't have to absorb what's on here. The only thing to realize is that there's sort of 2 components to these granite greenstone terrains. This stuff is all white. And down here are older granitoids. And those who are being intruded at the same time, the sedimentary and volcanic rocks were being deposited. Some of the volcanic rocks within that greenstone sequence are comagmatic with some of these intrusions.
that are coming at the bottom. So these are the older plutons. These red rocks are younger granites, and they stabilize with the continental block of about 3.1. And after that, it's a continental crust. The sediments and volcanic rocks that are part of the greenstone are in gray and brown and shown a few faults. They're just absolutely torn to pieces. I'll show you the slide in a moment. So the three components here are the greenstone, the granites, old granites, the young granites, and this stuff over here is proton covers. Relatively flat line, only 2.5 million or so. So there's the origin look like. We're in South Africa. It's absolutely gorgeous. Great place to hike. I'm standing on the greenstone belt here, looking out to the south over the granites. The old granites weather more rapidly because they're full of plagioclase, full of minerals that weather fairly fast. This horizon over here is the bright red rocks on the map. They're young granites, so they're full of case spar and quartz and more resistant materials. This is a basaltic dike, also of Archean age, but still younger than the granites. And so our geology is pretty well laid out in terms of gross sense. And most of the time I spent there, I spent in the greenstones. Can you guys hear me back there still? No? Okay. No?
That's hard to hear.
Okay, I have a tendency for my voice to drop off.
That's better.
I'll try to do better. Now, we were really lucky when we were there. We usually drive four-wheel drive vehicles into these remote areas, but one year we were able to met a guy who owned his own helicopter. Yeah, it was just a two-person helicopter. So he landed at the guest house. We stayed out in their barbecue, picked one of us up and flies out of the field, and then come back and get the other person. But he landed right in the front yard, in the lawn of the guest house, and brought us back there in the evening. So he dropped us off up on top of the hill, and here he's waiting for us. That's a helicopter down there. And boy, I'll tell you, that's an easy way to go. To get flown to the top of the hill. And it enabled us to map some very remote areas that we would have fronted for a long time back there, and we might never have made it. But you can see that this is really nice thing. Like up and down, there are lots of grassy areas, good outcrops in these resistant ridges, and most of those resistant ridges are sedimentary. Because virtually all sedimentary rocks are silicified. They're chirps, so they hardly weather at all. The volcanic rocks that they're intervened with weather much more readily, and they come the valley. That's a lot of the area of the Barberton Belt is forested commercial, which is great for the foresters and economics, terrible for the geologists. But we just have to deal with it. So you can see these are commercial pine or eucalyptus forests in the distance, and good outcrops. There's still a lot of stuff that's covered. So the matter is certainly the geology. Structure is really complicated. This stuff has seen 3.5 billion years of tectonism in our history. So you can see there are pieces sticking off like that, and this goes up here, and it's faulting in there, and this piece comes up and it's broken. Here's just an isolated piece wrapping around there. You just have to learn how to piece things together. It's like somebody took a piece of glass, hit it with a hammer, and it didn't muddle it too much, move things a little bit. And so you have to trace off and try to find these pieces that are connected to one another. Unfortunately, it wasn't random, so we can pretty much see what's going on. And finally, what we happened to be about midway through our work over there, they decided to take about half of the area we were working in, make a game reserve on. Well, first thing he did is he built a fence 10 or 12 feet high that for several years we just climbed over. Eventually we got in with the rangers and things, were able to visit in our own vehicle. And here we are out in this game reserve. You can see over here some animals. I've blown this area up. There's the edge of an animal right there. But what's interesting about this shot is 1, 2, 3 rhinos. Okay? And each of these rhinos is a mother and has a cat. So here we are getting our field view ready. This is in the morning. You can guess which direction we did not go. We did not go in that direction. We came back for orders. But we just got used to working around these animals and trying to be careful so that we didn't get too close. Stratigraphic column in greenstone belt rocks, and for several years we thought we could cross most of the faults and a lot of the faults, but at least we could understand what the stratigraphic column is. And basically, that greenstone belt has about 15 kilometers sedimentary and volcanic rock. The lower 12 kilometers is mostly volcanic rock. The dark purple are ultramafic volcanic rock. So yeah, lots of ultramafic rocks here in California, but there aren't any of them that are volcanic. They're all mantle-type material and freeze up tectonically. Back then, the Earth was so hot that it was producing ultramafic lavas erupting at the surface. About a 50% melt of the mantle that produces ultramafic rocks, and they come out from these thick sequences of rocks. We call them, they are called camaions, and they're true ultramafic rocks. The light colored, the mauve, light purple rocks, they're basalts, normal foliated type basalts, and orange units on mudcrust, basites and things like that. So I have a good assemblage of volcanic rocks. All of these little black units are silicified sedimentary rocks that are within those. And it's those black units that I've really spent half of a lifetime studying to try to tell us what the interesting thing about them, the reason they're so good. If you look up at the top, you can see closest to the classic sandstone and lava. It may not surprise you to know that water ran downhill in the however different it was, water still ran downhill. So the basic features we see in classic sequences are the same. Cross-cutting, flat lamination, signs of water moving downhill. But these little tritigrades have no siliciclastic sediment at all. There's no uplift, no deformation, no source areas of older rocks. There are 3 kinds of sediments in these. There are ashes that came out of volcanoes. There are biological sediments, and there are chemicals from out of the ocean. That is where we wanted to go, to find out what the ocean was like, and the atmosphere was like, and the life was like. And we didn't want to go to those siliciclastic sediments. They were derived after uplift and orogeny started. They were pretty much modern day siliciclastic sediments. So I'm going to show you a couple of slides in the volcanic part of the sequence. Trade of preservation. These are lava tubes, just bulbous linear tubes of the salt. They look as fresh as a lava tube you'd see up Hawaii. Pillows with radial pipe vesicles around the rims. These are pillows of the ultramafic rocks, and they didn't form pillows very well. They had a viscosity that was about that of water. It's kind of hard to make a pillow. Something at such a low viscosity. You need something that's a little bit more viscous. So these tend not to form great pillows. They really come up ultramafic lavas. But other than that, they just absolutely stunning pillows through all of the basaltic sequences. Eruption was almost certainly by major volcanoes like we see in terrains today, forming these sea flows coming out. The commodity lavas are so low viscosity that there are lots and lots of flows, volcanic flows that go for tens of kilometers. They're less than a meter thick. There are plenty of lava flows that are 50 centimeters thick. Because they were just viscous like water and they ran out and left you with a little residual. So most of these rocks are mafic, ultramafic. There are these felsic units that represent something quite different. They represent something that is more like felsic units today. It's something you find in volcanic arcs and it's something you find over in the basin. One of the things they do, they look more viscous lava, lots of fragmental material, so you're like standing volcanoes. So we have plenty of evidence that there were violent explosive eruptions of these felsic magmas, and they generated lots and lots and lots of breccias, conglomerates composed of this material, flanking aprons around the volcanic centers. And the only slide, those of you who know me will see, of turbidines. Those are turbidines, composed of felsic, silicic volcanic material that rumble down the side of an Archean vent and left you with turbidites and the subaqueous environments around. So it's a really nice assemblage of volcanic features we can see in these deposits, ranging from basaltic features to felsic features. And I challenge you to find, they look like something out of the Cenozoic. This is something that is not very complicated. It's for everyone to do. It took a long time. When we published my first paper back in the 80s, it was grounded through. We had a couple of discussions with nobody persisted, and by about 2000, people come around, and that's when you got some almost degree of terrestrial value from the planet all of a sudden. Yeah, exactly the same. But if you analyze pressure drift, almost like meteorites, it's possible. Almost like meteorites. They're not terrestrial. And so the one thing that began to do is people finally do all of the things, not all of the things, but many of them we must have brought in and realized that it's from on word. We discovered the name impact material. Numbered up here, you can see S1 up through S8. They're numbered in the order we found them, not in the stratigraphic position. We didn't want to have to renumber them every time we found a new bed. So we just numbered it in the order that we found them. S1 did happen to turn out to be the lowest. It's 3472, 2,472 million years old. And the youngest up here is 3225. So we have a good record of impacts over that interval. We don't know if we're missing some down here or if the flows overwhelm anything that might have been deposited through impacting. We've just not found anything down lower than that. The impact layers look like sandstone because they're made up of ejecta. So you get in these nice layers of chert. A lot of it's biological material, organic, it's chert, same thing over here. But here's a layer of sand. But as soon as we cut thin sections of these, it knocked ourselves because it was not ordinary sand. First of all, when you cut a slab, sand-sized material, but my goodness, looks like a bunch of pool. Spherical particles. They're BB-sized spherical particles, and when you look, if you have questions, feel free. Okay, here's what they look like in thin section. Some of them have internal crystallites. You can see faint crystals here. Some of them have rims, some of them have what were vacuoles inside. These form from rock vapor clouds. The impacts are so large, they vaporize large volumes of target rock and bolide. Spread around the earth as a rock vapor cloud condensed to form droplets. The droplets solidified and rain down on the surface of the earth. There's one of those at the KP boundary though. It's 3 or 4 millimeters thick. The ones that we have in Barberton are commonly 35 centimeters thick. These are very large. We've used other things than just thickness of the beds to verify the size of the impact. These impacts are between 20 and 50 kilometers in diameter. Take it down to there, impacting it 10. That's one, that first lowest bed. We found it in Western States. Exactly the same horizon. In Western Australia, when we get up to the top of the sequence, some of the upper bed, begins a really thick section of calcium volcanic rock. And I'm assuming I have to look through all of that. That's fine. I know others do too. But it's not a matter of they're not being there. The material layers are best preserved in quiet water environments. And more active environments, it's often unnerving. Here you can see some of these friels about 1/10 of a millimeter across. You can see these quench crystallize. That looks like a little dendritic thing. Something you see in your windshield, frosted really come out quickly. And that's exactly what happened. Quenched. Came out of a vapor cloud, quenched to form droplets, and then quenched to form these internal crystallites. Here you can see 2 of them was merged. You can see some of the internal crystallites. These crystallites don't have the same composition they did when it started. All of these have been replaced by silica and others that were preserved in the morphology of the original components.
What's the white surrounding the spherules?
Pure silica. This is in a chert. This is in a chert matrix. Another bizarre layer has bimodal spherules. Some of them large and now composed essentially of pure silica with coatings of chrome-rich micaceous material. Other small ones are made up entirely of that micaceous material. We think we might be dealing with sort of the fall of material from 2 different parts of an impact vapor cloud, very often different parts have very different compositions, or things that may have come out sequentially in evolution of one of the vapor clouds. These vapor clouds are condensing and probably behaved a little bit like magmas, and that some things condense first and other things condense later. And then lumpy spherules, these are things where it looks like you aggregated a bunch of particles that were originally soft in plastic to form some bigger particle associated with this one. These are all sort of bizarre.
Do you have any idea of how long it took one of those vapor clouds to fall and condense? Minutes, hours, days?
Probably it took a while because they sort of have to they disperse over long distances, and that probably took hours at least. And then they can do numerical modeling, but that's so dependent on the parameters you put in. But probably hours to at most a few days. Virtually all of these impacts are so large, they're accompanied by enormous tsunamis. You uplifted the ocean crust, you generated a huge wave transit. As near as we can tell, circled the earth. And so in a lot of places, the spherular beds contain all sorts of material from the underlying rock that have been ripped by these tsunamis. So instead of having a nice pure spherular bed filled in quiet water, the tsunami simply ripped up the spherules and worked them. mixed them with chert, and the greenish stuff is commodity ultimated volcanic rock performing these more wretched type of beds. But they're also good indications of impact. And just for your, this is a KT boundary layer. Okay, so here's the boundary clay right here. So the whole impact zone is right there. A few centimeters thick compared to the thing we're looking at, but counting the spherical layers and other fallback layers and tsunami beds, they often get to be more than a meter. Okay, just emphasizing bigger ones. You really fractured and compressed some of these spherules to scatter the upper layers of the earth. This is, I'm in a helicopter, I'm looking down on beds dipping toward me. So this is a bed, it's relatively even, but it's looping over a ridge. It's just the outcrop perspective. Down is away from me, and you can see they're relatively continuous outcrop here. But look at all of these things down here. Those are all dikes. So you shattered the crust by the impactor, and these layers here, which are black chert and black chert, just that black chert was soft gluey material and it's all fractured in the crust and it developed bigger. But it doesn't go up into the overlying sediment because it wasn't there. Two of the largest impactors were S2 and S3. These two, S2 and S3 up here near the top. Interestingly, you can see that S2 lies exactly in contact between 300 million years of anthropogenic volcanism and the beginning of deformation in the belt. So we're pretty sure that that deformation wasn't triggered by the. But we can model the size of the impactors and estimate the size of craters from the amount of material you can see in these impact layers. S2 and S3 were probably between, the craters were probably between 350 and 900 kilometers across, which is this Marinataurus here is 330, their embryo is 1120, and a bit larger than the S3 impact. So we're talking about lunar Maria sized craters that were on the Earth. The crater, the impactor that produced Maria and Holland, the other side of the moon, is a very famous impact structure, was about 50 kilometers across, the same as the size of this. So, if nothing else, the Earth was a good place to live because of now, they were coming down on a daily basis. You could probably buy a piece of property and build yourself a vacation house, stayed there quite comfortably for a long time. But they were coming down at a frequency that was thousands or tens of thousands or hundreds of thousands more frequent than we have today. And these were big dikes. They were coming down frequently. They were having profound effects. Not only did they probably affect tectonics, but they probably, some of these were big enough. 50-kilometer impact would probably deliver enough energy into the atmosphere to heat it up enough to boil off 300 meters of the surface water vapor. That would be delivered into the atmosphere by the impactor, and all of the energy blasted back up, heat up the atmosphere, boil off the surface layers of the ocean. If you lived at 400 meters, you wouldn't know anything happened, except pressure would go. Because you got rid of the upper 300 meters through evaporation. Okay, so we have some deposits, some crusts, some silica crusts that we're studying in these belts that we think represent essentially flash precipitates out of seawater, resulting from the evaporation, rapid evaporation of the surface. And this evaporation could have lasted for some time. The length of time the water stays as a gas and as a vapor as a function of the size. And it could have been for tens to hundreds of years.
Do you have an idea of the depth of these craters?
No, but they're relative.
Okay.
They were modeling them based on the size of them. If something that hit us and we could see the crater, we would be about to be done.
Are the cereals primarily of crustal origin or man origin?
Yes. There are spherules that are essentially common. There are spherules that are much more silicic. They end up mainly in pyroxene. Some of them might have been hydrophytes. There's everything on the surface, near the surface, has the potential to be replaced. So yeah, you can see the different composition of spherules. Some of them now are pure silica. That's replaced some pure silica to start with.
I'm interested in the relative quantity because ultramafic minerals are not stable under surface conditions.
Well, yes, depends on how long. I mean, we have all of the these rocks. Rarely, it's still on. And melting collisions that still observe what appears to be a plastic. They have recrystallized. So yes, ultramafic minerals are metastable, but they can last. And with the temperature regime, if the surface was hot, as I mentioned in a moment, certainly the hot temperature and the temperatures generated in the consequence of the impacts would have promoted them.
Do we know anything about the CO2 concentration, which would have intense weather?
Only thing I'm going to talk about it this evening, everything we have to really estimate CO2 is there some of that. And again, the insolence, but by doing interfacial analysis and crystal, you determine the evaporate the mineral on nothing, which is sodium and carbon. Here's the nopolite that evaporates today because the CO2 level in the atmosphere, concentration of CO2 is too low. You do get nopolite formed in interstitial cavities in sediments below where there evaporates. Rolling tunnels that they used to move water from hot springs to gas have nopolite in them because you can fill up the gas with CO2 phase, but it doesn't in the family.
So we had very high CO2.
That's probably what I'll talk about the temperature. I'm gonna whiz along. I really want to see.
Coming up on 8:30.
Yeah, I know you want to. Okay, I'll assume you're on the front page. Let's. There. We use church as quite material yourself in solution. How do we add yourself? Did we like the conversation? And I'm not going to get into a big discussion of that. It's too much for this. But if we have seawater with isotopic oxygen, isotopic composition, if you precipitate silica out of the seawater, the composition of the silica will lie along this lines. And where the point of the composition of the silica isotopically lies, where that is a function of temperature. So in modern systems, composition of silica is pretty close to 32. Partially on the terms of the oxygen comes up. And as you can see, as you go up in temperature, you change the composition of the silica. We've used this, we've used all three up to steps to estimate the composition of the temperature that puts that solid form was about 70 plus or minus 10%. We practically go and figure out something to get on. We have
We did all sorts of tests to make sure that the there's nothing, rework patterns from the skirts, and some of the other sequences, they're carried, they have some signature with them. So we're pretty sure that it comes from hot. Well, these very automated models, that is plastic. This is service, from the big island, the software for the platform. But they still have mass big amounts of them. But commodity ice is automated blocks having a viscosity of water. And when volcanism stops, and the subsidence and the volcanic mass, massive subsidence, you go on the surface and you get microbial rings. So this is a microbial net. In the modern world, of course, pretty much like all the microbial nets that were developed in the volcanic surfaces here. And when we look at when we look at rocks, we get these shirt layers alternating with carbonation matter from we cut thin sections of that carbonation matter. As stuff that almost is certainly preserved microbial needs. Carbonaceous wisps and drapes. There are big carbonaceous particles, probably made of mat-like material that can be ripped up by storms and rolled around. There's just a rich array of carbonaceous matter. Carbonaceous composition of this stuff is commonly in the range of minus 28 to minus 35, which is biological activity. Layer fragments, coatings and surfaces, and here and there. All produced by microbes, all produced as you can tell by one cell. It's just single cell, non-nucleated. Okay. So, the world before 3.2 billion years ago, truly no place for an old man with aliens getting smacked by meteorites, getting hot, and there are a number of other things that go along with that. But the only guys who can survive that with thermophilic activity, like those living in Montreal. All right. Thank you very much.
Lights more, please. Take a couple of questions, then we'll end the meeting. So who's got a question back here? Go ahead.
I really enjoyed the map showing the placement of old terrain and I'm just thinking about it. When I put those guys together, Australia, Africa, and Arctica together, you kind of see there's going to be some continuity, and then all of a sudden it's like I realized, so this is pre-Kratos. Yeah. So were these part of the same structure, or are these individual like islands out? It's really very interesting. The three really. Oh, I'm sorry. Yeah. It's very interesting. If you look at the three protons, they're known to have rocks in the back. This carbon belt in South Africa. There's a block in western Australia for the Pilbara block. Then there's a block in India, a single proton. It's not the same. If you put those back in terms of Gondwana land, they're much closer together than they are now. Okay? And there just isn't any other stuff that old around. Issue is older. But rocks of that age, real issues also Princeton. That's in green. So we don't know whether, and
And it's Barberton and Kilburn in Western Australia have very similar thrust activities. But you know, we don't know. Well, back in early Earth history, there was a time in early Earth history where events over the Earth were taking place. Events were taking place all over the Earth at the same time. Accretion, melting form of global magma ocean, differentiation of the core, formation of the atmosphere, late heavy bombardment. These happened all over the Earth at the same time. So are these rocks similar? Because we were still living at a time in Earth history when the major events were occurring on a global basis? Or had we passed to a time in history when the events were localized and different, but these protons just happened to be close to one another? Okay. We don't have enough stuff to do.
Very good. Thank you again. We have a very small token of our very large esteem. So here's an NCGS mug.
Oh,
Thank you
thank
very
you.
much.
I love mugs. I have a, yeah, thank you very much, everyone. All right.
Yeah.
Quick question, hopefully, temperature. We're measuring 70
Yeah.
in the church. You would also said bombardment covering the earth with vapor on it. The church is a different part of the earth.
Yeah, that's in between the, it's not, we've tried to date some